Dear students, welcome back. And again, we are going to continue with the laser. So in the first class, we had seen the different coefficients given by the Einstein. Then in second class, we had seen the relationship between those Einstein coefficients. And we had also seen that how we can use those Einstein coefficients to emit the laser beam. So what can be the condition for the emission of the laser beam? That is the condition for amplification of the light. This is what we had seen in the previous class. So now let's start with today lecture, and today we are going to deal with the requisite of the laser systems. That is, what are those conditions which should be used for the emission of the laser, and that is called the requisite of the laser system. The first among them is the population inversion. So I had explained you what is the population inversion. If the number of the atoms in the excited state is more than the number of the atoms in the ground state, that is called the population inversion, and which is not a natural system. It is against the thermal equilibrium conditions. So we'll look into that. Then we have the pumping. That is, to produce the population inversion, we require to have the pumping. Then we have the active medium, the medium through which we are going to have the lasing actions. Then metastable states, we'll look into that. And then finally we have the optical cavity, or that is also called resonant cavity. All right, so this is what we are going to look into in today's lectures. So let's start with the population inversion. All right, first we are doing with the pumping. So let us see what is the pumping. So as I explained you, to create the population inversion, we require to pump the atoms from the lower energy level to the upper energy level. So here in this diagram, I have taken the two energy levels. This is your upper energy level, and this we can call as E2, excited energy state, as we have seen in the previous class, right? This we can say as E2, and this is your lower energy state, E1. So what we require to do is the atom is to be taken up from the ground energy state to excited energy state by giving the photonic radiations on this. By giving the photonic radiations on this, these atoms is required to be taken from ground energy state to the excited energy state. Now, energy state is not like a laser line. It's a spread one. So here this is your lower energy state, and we are calling this your ground level, and this is your upper level. Within the ground level also there are different sub levels of the energy, maybe the detail about which we'll see in the quantum mechanics. All right. So from the lower energy state, what we are going to do, we are going to give the energy, photonic energy, to these atoms which are in the different energy state of the lower energy, and then these atoms is going to absorb this energy and it is going to move into the upper energy level, and that process is called pumping. So what we are calling the pumping, in population inversion, the atoms has to be raised continuously to the excited state. It requires energy to be supplied to the system. The process of supplying the energy to the medium with a view to transfer it into the state of the population inversion is known as pumping. So the process by which we are going to establish the population inversion is called pumping. Now there are many types of the pumping depending upon whatever of the laser we are going to use. So let us see some of them. Briefly we will discuss. Right, so types of the pumping. The first pumping we are calling as the optical pumping. Second is your electrical pumping. Third is your direct conversion pumping, chemical pumping, and fifth is the atoms to atoms inelastic collision pumping. Briefly, optical pumping is mostly used for your solid state laser, like the first laser that has come, a helium neon laser, right, ruby lasers. So those are your solid state lasers where the medium of the laser is the solid medium, right, and there we are mostly using the optical pumping. In the gas lasers, like your carbon dioxide laser, helium neon laser, all right, the type of the pumping that we are going to use is your electrical pumping. Then next is your direct conversion, that is the semiconductor laser, gallium arsenide, and there are many others semiconductor laser, right? So there the type of the pumping that mostly we use is the direct conversions. Then we have the chemical pumping. So in the gas also there are different type of the lasers. So within the gas laser also we have the different lasers. So within the gas laser, some of the pumping that we are going to use is your chemical pumping, and atom to atom inelastic collision. So in the gas we are using many type of the pumping depending upon the subdivisions, that whatever the gas we are going to take for the lasing actions. So these are the different types of the pumping, and let us briefly discuss some of them, at least the optical pumping and electrical pumping, which we are going to use in your lasers, right? That is your carbon dioxide laser, which is in your syllabus. And then again we have the semiconductor laser, so direct conversion. So direct conversion laser we'll see there when we'll start your semiconductor laser. All right, so let's see. So in case of the optical pumping, the red line that you are able to see over here, this is some of the solid rod that has been taken. So this is your solid rod that we have taken. This is nothing, this is your laser medium, right? So it is made of a certain solid materials, right? On this, here what we are going to do, here we are going to wrap with a helical tube. As you can see, this is a helical tube. So the helical tube has been wrapped all over the medium of the laser, and the two ends of this, and this is being filled with your xenon gas. This pump has been, or sorry, this pipe has been filled up with your xenon gas or some of the inert gas, mostly we are taking. And then we are going to give the electrical energy. This is your electrode. So here we have the electrode. So positive terminal and negative terminal we are taking. And then what we are going to do, we are going to give the electrical current through this. So moment we are going to give the electrical current, since here we have taken the xenon, so it will give you the white flash. So this entire tube will start glowing together at a time, just like your tube light, right? So almost same process is happening here also. So just like the tube light, the entire tube is going to glow all together from bottom to top. So since here the light that is emitting is the white light. White light is nothing, say composition of your many wavelengths, right? So entire spectrum, your right, that is in the visible spectrum, all the colors is emitted, and therefore its color is white. So now what is to be done is, as we have seen there, what is the pumping? We have to take the atoms from the ground energy state. This is your ground energy state to the excited energy state. So here within the ground energy state, we have the different sub energy state. So 1, 2, 3, 4 different sub energy state we can say. So atoms are distributed in all of them. So this we are calling this we are calling as E1. So this we have called as E1. Right. Similarly, we have the excited state. This is your E1. Similarly, we have the excited state. So within the excited state, there are other sub-energy state. So these are your sub-energy state, right? And then the atoms is to be brought from, let us suppose from this energy state, I want to bring the atom over here, right? Again from here, I want to bring it over here. Again from here, I want to bring it here, right? So what we are finding here, we are finding the different sub energy level within the energy state E1. So here, if I'm going to take the energy gap between these two, again let me show you with the red light. If I want to show the energy gap between these two, so energy gap as you can see is little more. But if I want to take these two, then it is little less. If I'm going to take these two, there is a further less, and therefore we know energy gap equal to h nu, right? So what we require, different type of the frequencies required. So here what is happening is white light is coming and it is going to emit the different type of the frequency, right? And entire frequency is going to radiate this energy state is getting radiated by all the frequency, and therefore corresponding frequency is being used to transfer, or frequency you can say wavelength, nu equal to c upon lambda. So different wavelength is being used to transfer the atoms from lower energy state to the excited energy state. So we can have the blue component is being used, or the green component is being used, or yellow component is being used. So whatever the component is being used, so that component of the energy will be used, and of course the rest of the energy is getting wasted, right? And in this way the atoms will move from your ground energy state to excited energy state. So this is what I'm going to look into this. So let me erase this so that we can understand this properly. All right, so here I have taken graphics. So what I'm telling you, the same thing has been explained over here. So the here from the ground energy state, the atoms are being taken, or the electrons are being taken from the ground energy state to the excited energy state, like this, ground energy state to excited energy state. So how we are going to do? Here we are going to apply the pump. So with the help of the pump, that is, pump is nothing, this is a radiative energy that we are giving, right? And by absorbing this energy, the atom is moving here. So here it has been shown here, you can see here. So atom is absorbing the energy and it is going to the excited state. Naturally, from the excited state, again it is going to come back after some time. If you are not going to do fast within the interval of 10 to the minus 8 to 10 to the minus 10 seconds, right? Then the atoms is going to come back in the ground energy state. So this type of the pumping, right, where we are going to use the flash lamp to pump the electrons or the atoms from the ground energy state to the excited energy state, is called optical pumping. Let us see another one. And this is your electrical pumping. Let us see this diagram. In case of the electrical pumping, the laser medium, the medium is your gas. So what we have done here, the one tube has been taken. As you can see, this is a tube, and in this tube is sealed from both the sides, right? And this tube has been filled up with the gas. So this entire tube has been filled up with the gas. Whatever the gas it may be helium, neon, or neon argon, whatever the gas is there. So it has been filled with the gas, right? And the two terminal of this has been attached with the power supply. As you can see, these are your electrodes. These are your electrodes. So we are giving the power to this. So naturally, what is going to happen? The gas which is there, the gas is going to be ionized. So the moment the gas is going to be ionized, we will have a production of the electron and your corresponding positive charge. Electron being lighter, it will move very fast. So, and of course here the type of the energy that we are giving, that is the voltage that we are going to provide, is very high. So here this voltage, here the voltage that we are going to give is normally very large voltage we are giving here. So electron is getting that is, this gas is getting ionized, and electron start moving very fast. So during the movement of the electron is going to make the collision with the atoms of the gas, and those atoms will also be excited, right? So in this way, what we are going to do, with the collision of the of the electron with the atoms, right, the atom again then in turn is getting ionized, and again it will be liberating you some of your electrons, and in this way the electron is being used to excite the atoms from the ground energy state to excited energy state. So what we are going to do here, we are producing the fast moving electrons. Electron is making the collision with the atoms, and then atoms, by receiving those energy from the atom, is moving to the excited energy state, and that type of the pumping is called electrical pumping. Why we are calling electrical pumping? Because we are going to here discharge the gas by the electrical method, and therefore it is called your electrical pumping, right? So this is what is happening in this case. So by absorbing the energy from the electron, the atoms are moving from the ground energy state to excited energy state. Naturally, again from the excited energy state it will come back, right? And in that process, some of the energy is getting released, right? It may be getting released by the stimulation or spontaneous. That we'll see again in detail when we'll again start the emission of the laser beam, and the two of the lasers are in your syllabus also. So there we'll see. So these are your pumping. So first requisite that we have seen is pumping. Now let us see the second requisite. The second requisite is your active medium. What is the active medium? As I explained you, any laser you take, the laser may be made of the solid, or it may be made of the liquid, or it may be made of the gas, it may be of the semiconductor, whatever. So the medium, that is the atom with which that laser is made, right? What are the type of those atoms, whether it's a solid state, or it's a liquid state, or it's a gaseous state, that will tell you about the medium, right? So here, let us suppose here we have taken the solid medium. So this is your nothing. This will call your active medium. This medium is called your active medium. Not exactly the active medium. This is your laser medium. What is exactly active medium? I am coming, right? So here we have what we have. Here we have the huge number of the atoms. As you can understand, if I give you the example of the copper, 1 gram per centimeter cube will be containing in nearly 10 to the power 29 number of the atoms per centimeter cube. So 10 to the power 29 number of the atoms per centimeter cube is there. And if let us suppose you are taking the laser of nearly 50 centimeter and 5 centimeter in width, right, you can imagine how many number of the atoms are there. So in this medium you have the huge number of the atoms, right, and those are called your active medium. So a medium in which light get amplified is called active medium, right? So this is the medium in which we are going to use certain process by which the light is getting amplified, and that will call your active medium. So as then again I have already explained you, the medium may be your solid, liquid or gas, or we can also say semiconductor. Now out of the different atom in the medium, so what I'm telling you here, this is the medium that we have taken. Now the medium, in this medium, let us suppose we have taken the ruby laser. So what is the ruby laser? Al2O3, and that is being Al2, so aluminum, O3 oxide, and that is being doped with your chromium, Cr3 plus, right? So what we are saying, the medium will have the different type of the atoms, right? So this is what I have written over here. Out of the different atoms in the medium, only a small fraction of the atoms of a particular species are responsible for the stimulation and consequent light amplification, and are called the active centers. Now this is important to understand. So we have the host of the atoms, large number of the atoms is there, but all these atoms are not directly responsible for the light amplification and in continuation of to the emission of the laser. Only few atoms are directly responsible for the emission of the laser by stimulator emission, and those atoms which is directly responsible for the emission of the laser beams are called your active centers. So those atoms are called active centers. So you should remember what is the active centers. The remaining bulk of the material plays the role of the host. It does not mean host has any less responsibility. That we will see in detail. Host and support the active centers. So other atoms are supporting in the process of the emission of laser. So some of the atoms are directly responsible for the stimulator emission, and some of them are just hosting, supporting that stimulator emission, and this entire atoms and the entire medium is called your active medium. So that was your requisite number 2. Let's see the next one, and this is again very, very important, and this we are calling as resonant cavity. Let's try to understand. Now as I had explained you, we can have the three types of the laser or 4 types of the laser. We can have your solid state laser, we have the gas laser, right, we have the semiconductor laser, and within the gas laser we have again many types of the laser, right? We have the dielectric laser. All right, so the types of laser here does mean the medium of that laser. It may be the solid, it may be the liquid, it may be the gas, it may be the dielectric. So that is the meaning of the types of the laser. Now the medium, whatever is the medium, the both side of the medium is being closed by the mirror. Both side of the medium, if it is a solid, there we are putting a mirror, and even if it's a liquid, there also we are putting the mirror. In solid, we can put directly the mirror. That is what we can do. The two ends of the solid is being polished, and that itself act like a mirror. But if you have taken the gas laser or the liquid laser, you have to put the mirror separately. Anyhow, what we are going to do, we are going to put the mirrors on both the ends. One of the mirror will be 100% reflecting, and the other mirror will be partially reflecting. So here this mirror that we have taken is your 100% reflecting, and this is your partially reflecting. Now what should be the value of the partially reflecting? It again depend upon what type of the laser we are going to use. So forget it. So don't go on the what should be the value of the silvering in case of the partially reflecting. It can be 90%, it can be 95%, it can be 98%. Forget that, right? So both end has been enclosed by the mirror, and the moment you have enclosed the two sides, right, by the mirror, it will be called as optical resonator, or it is also called as cavity. So as now you can see here, this is your active lasing medium. So this is your lasing medium, right? So this lasing medium has been covered by the mirror on both the side. For the pumping, here we have used the power supply. So the power supply is being done, right? So this is how we are making the resonant cavity. What is the action of the resonant cavity? Right, so that we are going to see in the next slide. So this is what I have written about the resonant cavity. You can read it. It consists of the two opposing plane parallel mirrors with the active materials placed between them. One of the mirror is semi-transparent while the other mirror is made completely reflecting. The mirrors are set normal to the optic axis of the material. This structure is known as Fevry-Perrot resonator. If it is particularly the solid state laser, then this structure is called your Fevry-Perrot resonator, right? All right, so this is your definition of the resonator. So what you have done, the active medium from both the side has been closed by the two mirrors. One of them is 100% reflecting, another is your partially reflecting, and that constitutes your resonant cavity. Now let us start and the working of this resonant cavity, because it's very important. Now let us see. Now here I have shown you that this is the active medium that here we have taken. This is your active medium, right? So this is your laser material. Laser material is your active medium. It can be the solid, liquid and gas. Both sides you have the mirror. So this is your one mirror. This is your another mirror with the transparent centers. All right. So one of them is partially silvered. Now here, now you see, now in this, here we have the atoms. So in the, what you know, that in the normal temperature, most of the atoms are concentrated in your ground state. So these are your different energy state within the ground energy state. So from the ground energy state, you have to give the pumping, and with the pumping it is going to move to the excited state. So this is what has been shown over here. So the pump is on and the photon has started moving, right? Or sorry, the atoms has started moving to the excited state by absorbing the energy from the pump, right? Now what will happen? Now the moment has come over here, immediately you will have the spontaneous emission. So this is what has been written over here. So immediately within the interval of 10 to the minus 8 to 10 to the minus 10 seconds, you will have the spontaneous emission. And moment you are getting the spontaneous emission, so the atoms or the energy is going release in the different directions, right? So let us suppose this is atom number 1 which is coming. This is how the photon is getting released in the medium. This for your second atom, right? This in the another direction. This is your third one. This is another direction. This is your fourth one. It's another direction. So what is happening? We have got the photon which is getting in the different directions. But in some of the photons may be exactly in the direction of the optic axis. So let us suppose this is the direction of your optic axis of the laser, exactly in the in between. So let us suppose this is the direction of your optic axis. So those photons which is in the direction of the optic axis will be used to stimulate the other atoms from the excited state, right? And other photons is required to be expelled out from the medium, right? So to expel out those photons from the medium, here we have open cavity. So both the side, upper side and lower side, as you can see, is open. So these photons, those which are not in the direction of the optic axis, will be coming out from here. It will be coming out from here. Then we have the one of the mirror is semi-transparent, and if it is not exactly inclined in the direction of this, that is also getting expelled out from your that medium. Some of the photons which is in the direction of the optic axis will also come out, no problem. All right, so now see what is happening. So now you can see slowly the photon intensity is building up in the direction of your optic axis. So if this is the direction of the optic axis, if this is the direction of the optic axis, so in the direction of the optic axis, the photonic energy is building up. How it is building up? One photon is going to excite the one photon in the excited state. Then you will have the two photons. Two photon is going to again excite another two atoms. Then you will have the four photons. Four photons is going to again excite another 4 atoms. So you will have the 8 photons. So in this way, slowly the photonic density is augmented in the within the medium, right? And those photonic energy which is not in the direction of the optic axis is coming out from the medium. So this is the slowly, so many times it will do to and fro, to and fro. Now in that process the photon has come over here. Now again this photon will be reflected back. From here it is getting reflected back. So as it is moving in this direction, again in the return direction also it will start exciting those electrons. That is stimulation will start. So again from here stimulation will start. Again these photons is going to return back because you're 100% silver. Again it is going to return back, and in this way it is going to do to and fro, to and fro, to and fro within this cavity, right? So then what is happening? Slowly now again you can see over here. So here first you see here the density is again increasing. Then if you come here, the density has largely increased in the direction of optic axis. Finally most of or all of the photons will be in the direction of the optic axis, and all other has been expelled from the medium or the active medium of the laser. And in this way all these beams can be superimposed and a resultant beam will be coming out from this, and that will be your laser beam, right? So now as you can see all of them are in phase, so all the beams are going to be superimposed in one particular phase, right? And in this way this is why the laser has got highest coherence. You have the two type of the coherence, temporal coherence and spatial coherence. Laser is the only source which maintain both type of the coherence, right? Even if you must be doing your experiment with your sodium lamp, in case of the Newtonian experiment, there the coherent length is very small and you have the only one type of the coherence. But in case of the laser beam the coherent length is in terms of thousands of the kilometer. But in case of the sodium lamp it is just in terms of the few centimeters, 22 centimeters or 40 centimeters, like that, right? So this is because of the entirely all of them are in the one phase when the laser beam is being finally composed of. Now let's see further. So here I have shown the entire process again. So as you can see all these are your atoms. So these are your atoms which is in the medium, So some of them are in the ground energy state, some of them are in the excited energy state. So here you are giving the pump. So with the pump the atoms are going to the excited energy state. So this is how it is moving. Then here it has come to the mirror. From here it is going to be reflected, right? Again it will be coming here. So again here you will have the total internal reflection, right? So totally it is getting reflected. So again it will be coming over here, and in this way slowly you can see the photonic energy is being building up with the stimulated emission. So one of the photonic energy is being taken as your from the spontaneous emission. That spontaneously emitted photon is being used to stimulate all other photons, and the rest of the spontaneously emitted photons are being expelled out of the medium. It takes a bit time, right? So this is how we are going to make all of them in one particular direction of the optic axis, and this is called the final state, that is your equilibrium state, where all of the photons will be exactly in the phase, and that is the working of your cavity, resonant cavity. So if you don't have this cavity, right here, this cavity through which it can do to and fro, right, you cannot have all the photonic energy which is going to be in the same phase. So that is the working of your resonant cavity. All right, let's move further. And this is your final one. This is your metastable state. Now what is the metastable state? Now you have the ground energy state. So this you understand. Here you have the ground energy state, right? This is your ground energy state, and then you have the excited energy state. This is your excited energy state. Very close to the excited energy state, this I will again tell you in detail there. Very close to the excited energy state, there is another energy state, and we are calling as a third energy state, E3. This is very close. Only for the simplicity it has been shown with a little distance, because if I'm drawing it here, then I cannot show you the transition, right? But what I'm saying you, the excited energy state that we have taken E2, and the third energy state, which is called your metastable state, is very close to your excited energy state. Now what we are going to do, with the pumping, the atoms is being taken to the excited energy state. With the pumping, what we are going to do, we are taking the atom to the excited energy state, not in the metastable state, although metastable state is very, very close. Now here, since it is in the excited energy state, so it is not stable, right? So it has a tendency to look into the nearest better stable state. So just near to this, here you have a metastable state. It's very, very near, and this is why we are saying when the atom is going to jump from your excited state to the metastable state, there is no emission of the photon, non-radiative fast transition. So we are calling this a non-radiative. By non-radiative transitions it is coming. So it is so close that we say approximately there is no radiations, right, when it is coming from one energy state to another energy state. So what is happening, the moment the atom will come over here, its stability will increase because its momentum breaks, right? So its stability will be more, and now here it is going to stay for the interval of 10 to the minus 3 to 10 to the minus 4 seconds. What was the interval over here? 10 to the minus 8. In the excited state here, the interval was of this state was 10 to the minus 8 to 10 to the minus 10 seconds. But here now it is 10 to the minus 3 to 10 to the minus 4 seconds. Now you can imagine how much time of this state we have increased. So now we have sufficient time to do certain activity, and so that we can emit the laser, and that will again look into in detail. Right now, the stimulation we are going to do between the excited energy state, between the metastable state and the ground energy state. So now stimulation is not being done from the excited energy state to the ground energy state. It is being done from metastable state to the ground energy state, and this is how then the laser beam will be coming out. So what we are saying, a third energy state which has been inserted, right, between the ground energy state and the excited energy state, and very, very close to the excited energy state, in which the atoms are coming with the non-radiative transitions, are called the metastable state, right? So let us see what I have written. It is also an excited state, but have the lifetime of 10 to the minus 5 to 10 to the minus 3 seconds, right? You can also write 10 to the minus 4 to 10 to the minus 3 seconds. Population inversion occur in between the metastable state and lower state. So as I told you, the population inversion we are going to have, that is stimulated emission we are going to have between the metastable state and the ground energy state. Therefore, it has lifetime of more than excited state and lesser than the ground state. So naturally here you have 10 to the minus 8 seconds. Now here you are getting 10 to the minus 3 to 10 to the minus 4 seconds. So naturally it is very, very large. Of course, it is less than your ground energy state, where it is very, very stable, right? So this, the third energy state that has been inserted very, very close to the excited energy state, is called metastable state, and which is essentially required for the emission of laser beam. And in this way, I finished today's lecture. So requisite of the laser we have finished, and now we'll be looking into some more details before we are coming to the actual lasers. Thank you very much.